Today we are going to continue doing a couple examples and then add a little added something else to it, in that what we do when atoms gain or lose electrons in their electron configurations. What does that look like when we get into that? First, let's do some of the same things that we had been doing as a nice friendly reminder of how do I write out electron configurations. Again, as always, good practice, getting used to writing what or trying it out before I get to it can be very beneficial for you. Arsenic ends in what row? The fourth row. So it ends in 4p because it's in the p block. Regardless of where it ends, it has to start with what? 1s. Now everything that we do to 4p is going to have a full shell. After 1s comes what? 2s. After 2s comes after 2p it's after 3s. Okay, now here's going to be where sometimes we have this little bit of the, well, is it correct that way or is it not correct that way? I like it done the way it's written out on your periodic table. Therefore, after 3p comes 4s. And then after 4s, 3d. Okay. All the way through the D block. Then you count how many elements in the P block is arsenic, and it is 3. Then we get into the, well, now we need to know and draw the other part of it, and that is the orbital diagram. Orbital diagram is going to get probably pretty crowded. I'll resize this thing up a little bit. So with that, we'll draw 4 circles because it's in the 4th row. There should be 2 dots in the first one, 8 dots in the second one. Now in the 3rd ring, there should be a total of 18. Where do they go? How do you draw them? Is a little bit up to you on what method you use. I have 16, 17, 18. Then in the 4th row, 1, 2, 3, 4, 5. So it's a little hard to read on screen in class, but it is there. For strontium, we do not do anything technically new. we do the same thing that we have. We look at what row is it in. It's in the 5th row. It's in the S block. That's where it ends. Where it starts again is exactly the same place. If we continue all the way through, we will again, remember, everything up to that 5s is going to be filled. If we read it as it's our periodic table, 1s, then the second row goes through 2s, then goes through 2p. Then we're done, and now we go into the third row, 3s, then 3p. After 3p, you get into the 4th row. And remember, this is where the tricky happens. 4s. When we're in the D block, it's n minus 1. Because we have to go all the way through. Then comes the 4p. And then we get to our 5s. Then we ask, how many elements into the S is it? Well, you can only have 2, and strontium is the second one. The noble gas configuration can get rid of a lot of that repetitiveness. The noble gas configuration requires you to look at your periodic table. Look at what is the noble gas in the 4th row, not the 5th row, because we haven't got to it yet, right? You have to go to the one that is in the 4th row, and that would be krypton. Okay? You then put that in brackets, and basically what we're saying with the noble gas configuration, oh, that's highlighter. I don't want that. Noble gas configuration says all of that krypton has. Because it does. The only thing krypton does not have, 5s2. That's noble gas configuration. It's not very hard. You do need to know it for your mastering chemistry. Some people don't like it because they get confused by it. I accept either or on the test. If you know how to use it, use it. But don't put, like for helium, you can't put a noble gas core. That's the first one that you could, but it's not, nobody can. So lithium would have like He and then like one, but even that, it's like, really, are you missing out on anything? But for some of the very large elements on the periodic table, like lead, the noble gas configuration is real nice. Cuts down on a lot of writing. The orbitals, you don't get to do that with. You still have to write all of the circles. Oh, just wait till you do lead. And you go through the F block, and you have 34 electrons on your 4th ring. It's super fun.
Oh my god. Is it on the slideshow?
Yeah, you have to put 34 dots on a circle.
Nothing's
There you go.
impossible.
It's gonna look like just like a really thick circle.
It is. Okay, so there's 18 on that one. Then we put 8 on the fourth one. No. There. And then 2 on the fifth one. Sometimes atoms gain or lose electrons to gain what is called a noble gas configuration. This is what drives chemical reactions. It is the elements trying to gain or lose electrons to achieve the same electron configuration as a noble gas. Again, they are trying to achieve 8 electrons in their outermost shell. Outermost shell are the s and p orbitals. Because the p can hold a total of 2 electrons. I'm sorry, the s can hold a total of 2 electrons. The p can hold a total of 6. 2 plus 6 is 8. They're trying to achieve what's called the Octet Rule. And octa means 8, just like the octagon. Okay? Octa means 8. They're trying to achieve that 8 electrons in their outermost shell. When we deal with isoelectronic ones, we are usually only going to deal with the main group elements, and that would be groups 1, 2, 13 through 18. The transition metals will lose electrons, but their chemistry is a lot different, and we're not going to worry about that at this time. Okay? So we write out the same electron configurations, but now we're going to have to add an electron or remove electrons based on what is happening. And they're doing this to achieve the same electron configuration as a noble gas. And the only noble gas not to have 8 is helium. So there are going to be exceptions to the octet rule. We'll dive into those exceptions in more detail later on. So, some of the electron configurations that we have done, and we are going to keep these, we'll do these because we have done these before. But this time what's going to be new is the fact that we have either lost electrons, gained electrons, and we have to do based on what we have here. So when we look at, say, carbon, we know carbon has the electron configuration. Let's write a better 2 than that. Of 2s2, 2p2. But this carbon has lost 4 electrons. Because it's lost 4 electrons, it has an electron configuration of 1s2. Which would be the same electron configuration as helium. For oxygen, we have an electron configuration like so. But this time, we're going to add 2 electrons. To give us the electron configuration of that, which would be the same as neon. For phosphorus, we have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p3. It adds 3 electrons to give us the electron configuration of that. I just shortened it up and went with the noble gas core. Which, again, the noble gas core is saying that all of this is there. Because neon has all of the things that I circled in yellow. When I write it out for chlorine, we know that it has this. It adds an electron to give us the electron configuration of Now some might ask, where did it get that electron? Don't worry about that yet. Don't worry about that. Don't worry about where it got its electron. Just say, okay, it got an electron. Okay? We will get to a point where we'll worry about where did that electron come from. But right now, we're not worried about where that electron came from. We can just know that it got there. For calcium, we're going to shorten this one up a little bit. Let's go with the noble gas core of argon. Because if we look at the electron configuration for argon, it would be that. Okay. So what I'm saying is argon has everything that's there except for that. If I subtract 2 electrons, sometimes it can, I've seen it written out as just that. It's not suggested. That's not the suggested method. They, I know, would prefer that it be written out that way.